before I start, I would like to introduce a special guest of mine, Professor Ralph Parkman from San Jose State University is here. Ralph was a graduate student here, a doctoral student in the late 40s. He taught for a time in the department in the early 50s, and then he went to San Jose State College at the time to start the metallurgical engineering department, the department from which I was the first graduate. It later became a materials department. He sent more than half dozen of his students, many of who are here, up to Stanford for PhDs. Ralph is celebrating his 99th birthday, and I think he deserves a hand. So you've seen the book, so it's really about the people and events, at least some of the people and events that have made up the history of the department. In a way, so you haven't read the book, and now you're going to hear the talk about the book. It's sort of like watching the movie before you've read the book. And is the usual case, you know, the book is way better than the movie. So I hope you find the book better than the movie you're going to be watching here. So I would like to cover some of these events. Now, actually, even before a materials department was formed, there was a course that I want to specifically describe. It was called Metallography and Physics of the Metals. It was offered by Dorsey Lyon. And let me just read this. And this is the course description. It said, this is 1903 now, work will include a study of the microstructure of the industrial metals and alloys and of the influence of chemical composition, thermal and mechanical treatment upon their structure, and also the relation of the structure of metals and alloys to their physical properties. And I argue in the book, you could hardly create a better working definition of the subject of material science and engineering, at least for most of the 20th century. So we had a very, very early start. And for those of you who are metallurgical historians, I note here that Dorsey Lyon had studied with Albert Sauveur at Harvard, and some of you will know that name. Okay, well, the department in 1919, it was founded as a mining and metallurgy department in 1919. It was the predecessor, as I'll describe, of our department, and the first executive head, was Theodore J. Hoover. He was the older brother of Herbert Hoover, who, of course, was the 31st president. And here's a sketch of his. He was a mining engineer, just like his younger brother was, and he was mainly involved in extracting minerals from ores. And he also. The department joined the newly formed School of Engineering in 1925, some 6 years after it had been founded, and Hoover, the head of mining and metallurgy, became the dean of engineering and was the dean for some 11 years. Now, in the 1920s, there was work on various aspects of mining and metallurgy. I'm focusing on those parts that link into material science. Physical metallurgy was pursued in the 20s. Welton J. Crook was a key figure that many of you will have known. He graduated in geology and mining in 1911, and then started his career at Pacific Coast Steel and became a steel metallurgist. And his contributions in the 20s involved writing about and making inventions and getting patents and writing papers about the uses of steel in various applications, including oil drilling, oil bits, and the sucker rods for that. So that was the beginning in the 20s. Cutler Shepherd, another name that many of you will have known. Orson Cutler Shepherd was a giant within the department. He started his career in metallurgy and of gold and silver, and he became the future founding department of the material science department when it was created. He came to Stanford in the early 20s and got his mining and metallurgy degree in 1925. And shortly thereafter joined the faculty in 1928. And so he led students in metallurgy. He did a number of things. He brought X-ray diffraction to the department in the 1940s. He encouraged the development of transmission microscopy, and as I already said, served as the department head in the late 50s and early 60s. Here's an interesting picture of, that's Cutler Shepherd right there on the left with a bunch of his students. This is outside the back of the mining and metallurgy building. Some of you might recognize the texture of that wall to notice that it's in the back of that old building. And I like this picture because it includes Alden Greninger. Some of you folks will remember we used to use Greninger charts to measure the angles between crystallographic planes from the spots on Lowy patterns. And that's the Greninger of Greninger. He actually did that at Harvard after he left here. So he didn't do it at Stanford, but shortly thereafter, he was doing crystallographic work in alloys at Harvard and created the Greninger chart that many of us used. Now, I'll be talking about the department and the various school affiliations. I thought I'd show this little chart here to explain the kind of the tortuous history of the department. As we all know, it was founded as a mining and metallurgy department in 1919, and for the first 6 years, there were no schools at the time. There were few schools anywhere at Stanford. There was no school of engineering at that time. So it was a standalone department, as were many departments. Then, when the School of Engineering was organized in 1925, with Hoover as dean, the mining and metallurgy department became one of the 4 principal departments of that school. The and metallurgy was dropped for a while in 1929, and it became the mining engineering department, still in the School of Engineering. But the geologists were never quite happy about mining and metallurgy being in engineering. They thought it should be connected more to geology, which is connected to mining and so on. So there was always a tug of war about that. And by the late 40s, they managed to bring the mining engineering department to the new School of Mineral Sciences. So we left the School of Engineering, 1947, and joined the new School of Mineral Sciences. It's now the Earth and Environmental Sciences, Mineral Sciences. And we're there for about 10 years. Fred Terman, who had just become Dean of Engineering, was not entirely pleased about that, and he angled for years and eventually did bring the department back. It took on various forms. First of all, it lost its department status, and there were only programs in the School of Mineral Sciences. Finally, in '58, it became a full-fledged department. That's the department that Craig was talking about and that he joined and with that ENCO fellowship, and still in the School of Mineral Sciences. But by 1960, Fred Terman had managed to pull metallurgy back out of that school and into the School of Engineering, changed its name to Material Science, and then later, in '71, we added the and engineering. So that's the kind of tortuous history of the department and its various school affiliations. Just thinking of that time, here's the 1940s. Here's a picture of the faculty of mining engineering in the 1940s. And on the left is Cutler Shepherd. There's Welton J. Crook, the principal people. And then the others here, Humphrey, Schellinger, and Tickell, these 3 here, covered mining engineering, extractive metallurgy, and also petroleum engineering. Tickell at the time was executive head of this mining engineering department. So we were a part of that mining engineering. Whoops, I think I pushed the wrong button. There we go. Now, by World War II, or after World War II, atomic energy and federal support of research really came into vogue. And Cutler-Shepard acquired some grants from the Office of Naval Research, Atomic Energy Commission, and NSF also, for work on creep of metals in controlled liquid metal environments. And liquid metal corrosion was a key part of that as well. I think, this was partly driven by Hyman Rickover, who was interested in high temperature heat transfer systems for nuclear submarines. So there was a drive for that. And a number of students joined in this effort with Cutler-Shepard, including Ralph Parkman, as I've already briefly mentioned. But Thomas Paine was one of the key people to join in that effort. And he was kind of the leader of it. And Paine was the principal graduate student in this period. And it's just as an aside here, Tom Paine was later the administrator of NASA at the time of the moon landing. So he rose up through General Electric and later on became the NASA administrator. Now, in spite of the engineering relevance of this kind of work, in spite of that, as I've already mentioned, in 1946 or 47, the mining engineering moved to the School of Mineral Sciences and back with geology, something that Fred Terman was not entirely happy about. But he kept pushing on this, and by the 1950s, we're now talking aerospace and electronics, and I would say the coming of material science. And as I indicated here, Fred Terman really pushed to bring metallurgy back to the School of Engineering. He could see the need for materials in his school. Well, it was no longer his school. He was the provost at the time, but in the School of Engineering. And as I'm going to explain a little bit more, Sputnik in 1957 really provided the spark for this. But in preparation for this, Fred Terman, as provost, asked Bob Huggins, who was then an untenured assistant professor, to conduct a search for, we need more people, conduct a search for a faculty member in metallurgy. And so Bob did the usual thing and had, I don't know how many applications, and wrote to everyone and did a proper search. And he came up with 3 names, and he just couldn't decide among the 3. And the names were Oleg Sherby, I picture here, Dave Stevenson, and Vic Macris, for whom I could not find a photograph. So Huggins found those 3, and he was a dilemma what to do. And he went over and told this to Fred Terman. And he said, well, leave me the files. Let me look through these files. And so a few days later, Terman calls up Huggins and said, hire them all. Just take them all. And this indicates the aggressive, the bold nature of those times, and in Fred Terman in particular. Hire them all, and he did hire them all. And so we went from a faculty of 2. At the time, it was just Huggins and Shepard that were left, and we went from a faculty of 2 to 5. And also, in connection to this push, as I've already said, we moved back to the School of Engineering. So the Department of Metallurgical Engineering left the School of Mineral Sciences and became the Department of Material Science in the School of Engineering. So kind of a mixture of words there. And you all recognize this place here is the old Mining and Metallurgy Department. I write about it in the book. Later on, when it was renovated, it became the Peterson Laboratory, and that was the traditional home. Now, I've already alluded to the fact that things were happening in the late 50s, and the thing that really provided the spark for what happened happened on October 4th, 1957. Had I not shown you this and I asked you what happened on October 4th, 1957, half of you would know Sputnik. That was the day Sputnik was launched. And that people's hair were on fire about that. And here's just a short list. The President's Science Advisory Committee, PSAC, published an article just a few months later, Strengthening American Science. And there was something called the Interagency Coordinating Committee for Materials Research and Development that recommended that we build research activities at universities, not necessarily giving it to companies, but giving it to universities in the hopes that the future would be created by doing so. And eventually, the Advanced Research Projects Agency, ARPA, was created in 1958, and it was designated as the lead agency for this new effort called the Interdisciplinary Laboratory, IDL program, and it was created in 1960. The first universities were Cornell, Northwestern, and Penn. We didn't have big enough boots to make it the first time, but the next year, Stanford was included in 1961, and the Center for Materials Research was created. So during this very short period of time, the Materials Science Department was created, the Center for Materials Research was created, and we were sort of on our way to becoming something more prominent. Well, that led to just an explosion of faculty appointments. No time to tell what each one did. It's in the book, as I keep saying, it's in the book. You read the book, you know the book. Okay. So here are the people that were all appointed in the 1960s. And if you count them all up, we went from, prior to those three that I mentioned coming, we went from a faculty of 2 to a faculty of 12 in 10 years. So huge expansion there in a 10-year period, 1958, 1968. So it was a major change. Now, you, of course, you recognize me instantly right there. Right? You're not supposed to laugh at that. You actually, CB, you probably do recognize a little bit more, which makes me kind of sad. But there's Craig Barrett and the others. You see the names. All those folks were appointed in the 60s. Now, other things were happening. There was kind of a demise of the industrial research labs in the 60s, and we benefited from that. And here's just a list of the people: Dick Bew, Bob White, Bill Spicer, Bill Tiller, Ted Jabal, Clay Bates, all came from industrial labs. So the sort of the decline a little bit of industrially sponsored research, fundamental research, led to our benefit. And there's still the focus of all this was on material science, the science of materials. Now, let me just mention a couple of things that was happening in the 70s. One of the really seminal events was the founding of Failure Analysis Associates, later on changed to Exponent. This was really an important thing. Alan Tettleman was the key person. Here's Alan Tettleman. And John Shine and Marsh Pound and two others were involved in creating Failure Analysis Associates. And I indicate here that the capitalization, there were 5 of them, capitalization were $500. They each pitched in $500 at the Oasis, I think. In 1967, they all met at the Oasis. They pitched in $100 each. There's the capitalization. And when I last looked, the revenues were exceeding north of $300 million. So it's a huge impact. Here are the three principals from the department. And then here's a picture of Marsh Pound right there with several students, not all of whom, but many of whom worked with him in this failure analysis activity. Now, another event that happened in the early 70s, I call almost a Nobel Prize. One of Dave Stevenson's students, Herb Maruska, who had come from RCA at Stanford, developed really the first blue, it was really violet, light-emitting diode. And that was, they did that in 1972. Here's the reference. And this is significant because by mixing red and green and blue light, you can get white light, and that leads to flat panel displays, a very big deal. Here, in fact, is Herb Maruska here, and Bruce Liebert holding, in fact, this gallium nitride LED that they developed. I mentioned almost because in 2014, others, after this had been perfected, were awarded the 2014 Nobel Prize in Physics for the development of the blue laser. So Herb Maruska and Dave Stevenson and their colleagues came very, very close then. Now, I mentioned that microstructure was mentioned in Dorsey Lyon's first course. So microstructure has been kind of central to the field, and so I thought I'd show a couple of pictures. Up in the first half of the 20th century, and maybe a little longer, optical microscopy was the principal instrument for microscopy. And here's Welton Crook at his bench metallograph, and here's what we were all very proud of. This is probably in the late 50s, a new metallurgical microscope that we got. And here's Cutler Shepherd with a student doing some optical microscopy. But as Craig Barrett mentioned, by the 60s, electron microscopy was coming into play. And I mentioned before that Cutler Shepherd encouraged the development of electron microscopy. He worked with Ladislas Martin, Bill Martin, who was at Stanford in the electrical engineering department, trying to build an electron microscope. And here is Martin working on his electron microscope here at Stanford in the mid-40s. And I think Bob Sinclair tells me that Martin might have been the first to image some biological structures. And you've already seen this picture here. By the early 70s, we had microscopes, and there's our friend Craig Barrett. But when he left, he was replaced by Bob Sinclair, who brought electron microscopy to a whole new level, as indicated here by both Ann Marshall and Eileen Coe on using various modern microscopes. So microscopy has had a central role in the department. Now, here's another story to tell of this time. I call it solid-state electrochemistry and the coming of lithium-ion batteries. Bob Huggins, after he had done his work to create the department and create the center, he went on, took a sabbatical in the mid-60s and came back and started work on solid-state electrochemistry. And one of his first really seminal papers was his work with his student Wen on the thermodynamics and kinetics in the lithium-silicon system. It's the foundation for lithium-ion batteries based on silicon. And at the same time, in the early 70s, when Bob was back in Washington taking care of the interdisciplinary laboratory program, Stan Whittingham was one of his postdocs. And he carried on with Bob's students work on solid-state electrochemistry. And this is significant because 2 weeks ago, many of you know that Stan Whittingham was named as a co-recipient of the Nobel Prize in Chemistry for work that he did on titanium disilicide for lithium-ion batteries. That work was done at Exxon after he had left here, but he started his career with Bob Huggins here. And then about 10 years ago, Bob teamed up with E and one of his students and developed really high-performance lithium-ion anodes with using silicon nanowires. And the key thing was that there's huge volume expansion when you lithiate something like silicon, because its volume changes by 300%, a huge amount. And so by using silicon nanowires, you could accommodate this volume change and get many cycles of life in that way. Now, there was many other things. Many of you remember Oleg Sherby and his ultra-high carbon steels. He and Jeff Wadsworth developed, quite improbably, that ultra-high carbon steels that you would think would be brittle as heck, under the right circumstances, can be made super plastic. So here's an example of one of his ultra-high carbon steels. I think that's, if I can read it, it's 1.8% carbon. And for all of you who remember your steel phase diagram, that's a very high carbon content. And you expect that to just be dead brittle. But the way he did it, you can get this kind of this extensive superplastic deformation. And that led, they found similarities too, and that led to kind of the rediscovery of the art of Damascus steels, how one could work materials in such a way as to produce those. Now, it was not all work. It was fun and games too. Here's a picture in the book, taken from 1968. This team is the Dislocations, naturally, and they were the touch football champions of the intramural league here at Stanford in 1968, and you see fourth from the left there. There's our speaker, Craig Barrett. He's kind of hidden back there, and many others. The ones that are here. Well, not here. Fred Farrer is on the right, and Tom Reed and Bud West. I guess none of these. Bob Johnson is there. Where's Bob Johnson? Bob Johnson's right there. So anyway, that was a touch football league. They were very successful. Now there was also a famous 1.5-mile run. There was a challenge by the students to challenge the faculty on a 1.5-mile run. That would be 6 people, each running one time around the track. And so here's a picture of the faculty. Now, this is Steve Robinson. He was sort of drafted. He was a postdoc at the time. He was drafted to become masquerade as a faculty member. So there's Craig, Steve Robinson, the ringer, Dave Stevenson, Oleg Sherby, Bob Huggins, and Clay Bates. And then here are the students. I've got the names: Hugh Vanderplas, Mike Mruzik, Jerry Lawrence, Dick Lund, Mike Thomas, and Kim Mitchell. So they had this race. And here, in fact, is a picture of, it's mid-race, actually. Turgut Gur is standing here, and he's timing it. And at this moment, you see, this is Bob Huggins right here. You can't see it, but Dave Stevenson is right behind him. So Stevenson has given them the lead. So they're ahead right now, and the students are behind. But actually, the students won. Another thing that I write about, and I think is important, is about the pioneering women that have played roles in the department. For the first 50 years of the department, there was really only one woman to get a degree. And that was Janet Saft Briggs, who got a degree of engineer in 1933. And she went on to have a very successful career in the steel industry and was elected to the National Mining Hall of Fame. So a very prominent person. But after her, there were no women at all until the early 60s. And I just write the names of the early master's students that came there in the 60s. These were the very first, really pioneers, because they were entering this male-dominated activity. Also, about that time, in the early 70s, Carolyn Fouts, Alice Fisher Colbury were almost alone. We had so few students anyway, and they were just by themselves, fighting their way and earning their degrees, both bachelor's and master's in in Carolyn's, and then Alice Fisher-Colbury went all the way to the PhD, working with Artie Bienenstock. And just one other slide on this. Imelke Kinley arguably is the first woman, student of Craig Barrett's, first woman to get a PhD. So here's a little chart of the cumulative number of both men and women. And you see women start here in 1973, and there's hardly any. And they gradually go up. But still the change here is small compared to that. Finally, in 2004, Sarah Heilshorn became the first woman to be appointed to our faculty. And then not too long thereafter, Jennifer Dione, who will speak to you this afternoon, became the second woman on our faculty. So we're making slow progress along these lines. I mentioned, you've already heard this, but I mentioned Jennifer, it was announced, I heard it a couple of weeks ago, she received the 2019 Alan T. Waterman NSF Award, and it's the highest award in all of science for anyone under age of 40. So, though the numbers are small, though the numbers are small, the quality is high. Now, but I've been talking to you about research mostly, and it came with a kind of a neglect of the undergraduate program that I've already sort of hinted at. Here's the cumulative number of bachelor's degrees granted by the department as a function of time since kind of the beginning of time. And there's a period here where there were just none. We just weren't producing undergraduates. And that was not appreciated. and that led to a loss of one billet and a relatively flat faculty headcount for at least a couple of decades. So that had serious consequences. And in addition, we were slow, the department was slow, Craig knows this, to adopt silicon technology. We knew about it, but we hadn't contributed much to it. And that began to change in the 1980s. John Brobman was appointed for work on electronic materials. Stig Hagstrom came and did surface analytical work that was relevant to that area of technology. And Bruce Clemens came and started doing work on thin metal films, but thin film science and thin film technology. So we made some progress. Now, for a long time, a lot of us did work on mechanical properties, and it was mostly on bulk mechanical properties, not materials related to silicon technology. But that started to change in the 80s. And Paul Flynn came from Intel, with Intel support, and built instruments for measuring stresses in thin films as a function of temperature. So you could really monitor what was going on mechanically in very thin films. And I was involved in bringing nano indentation to Stanford, and that also had an impact on characterization of thin films. And then when Rainer Dausgaard came in the 90s, he developed interfacial fracture methods that would be applied to thin film structures, microelectronic films, but then later on found that the same methodologies were useful in studying the stratium corneum, the skin, adhesion of skin. So things were changing in mechanical properties, and I'll just also mention that Bruce Clemens brought the technique of measuring stresses in films while they are growing, while they are being deposited. And you can see from this little plot here, there's some measure of how the stresses are evolving as the film is being deposited. And finally, Paul Flynn, again, working with John Brobman, built a high voltage scanning electron microscope to be able to directly detect the voids that are created in interconnects and watch how failure takes place. Well, But still, in spite of those efforts, there were what I would, and I write about this in the book, there were troubles for an aging department. I already mentioned that there was almost no faculty growth here in almost a 20-year period. And then, about the time I became chair, which is right about there, you know, the senior faculty from the 60s were reaching retirement age. So the ranks were being depleted very, very fast. And so I was the one holding the bag. So my tenure runs from about here to about there. So, but they were smart enough to get rid of me. They said, oh, we don't want any more of that. So Brovman followed me, and Bruce Clemens, and Bob Sinclair served for many years, and Paul McIntyre, and finally Alberto Sorleo. And they were the ones who brought about this rebirth of the material science and engineering department. And it did involve an aggressive plans to make better contacts with electrical engineering, mechanical engineering, and just involvement of other engineering disciplines was a hallmark of that recovery.
When did Trilby retire?
Trilby would have retired probably in the late 70s. Yeah. I wish I had a way to retrack all of the staff people, but I haven't done that. So by the 1990s, we were getting ready for the rebuilding of the 21st century. And Sean Wang came with and has done brilliant stuff on using magnetics. Rainer Dausgaard, fracture and fatigue, which we badly needed. Fritz Prinz in manufacturing, and Paul McIntyre in electronic ceramics. So those were the beginnings. I call it the beginning. Rebuilding for the 20th century. The beginning happened in the 1990s. And then the explosion happened, another explosion here in this century, beginning with Mike McGee in 2000 and extending all the way to here, and two more are coming. So there's no time to describe all of these folks and their work, but if you just read some of these things, solar cells, photonics, biology, thin films, of course, biomaterials, nano photonics, energy production, storage, even, I can't read that, even neurotechnology, even. So big change. And I'll just end then with, you know, I observe here a kind of changing definition of material science. And what I would say is that there is a traditional definition put here in perhaps modern form. Let me just read it. The traditional definition would be the synthesis and processing and modeling and characterization of useful engineering materials to control their properties and behavior through the control of composition and microstructure. And I would call this engineering of materials, where you're engineering the material. Now, to that, I think now we should add, and here's the addition, it's utilization of materials and material science to address pressing and exciting societal problems in technology, the environment, biology, and medicine. And I would call this largely engineering with materials. So there's a different element that's come, and that has come in the last 20 years that has broadened and has led to all the excitement that you find. So let me just say thanks for coming and helping us celebrate a century of material science and engineering, and I hope you like the book better than this movie.